Okay, so 16.2 is on line integrals, and you've done a line integral already, which is an arc length. And arc length, you just sum up little bits of arc that are linear approximations to the curve, and you just add those up. So just as a reminder, arc length S was a single integral, not a double or triple integral, thank goodness, over a curve of the arc length differential, which is ds. And just as a reminder, ds was, that's just distance. And as you know, distance is rate times time. So if you have a vector function, like a vector valued function that gives position, let me go ahead and do it this way, where r of t is a position vector at time t.
Professor, I think your screen is frozen.
Oh, jeez. Nothing's going right. How about that?
Yes, that's better.
Okay. All right, so so r of t is a position vector, and you may remember magnitude of r prime of t is speed, and distance is speed times time. Oh Lord! Now it's that's my Amber Alert. How do I stop it? Did you guys get one of those? Oh my gosh. Okay, so let's keep going. Wait, let's just read it while we're at it. This is a public search. Oh, it's gone now. I don't know where it is. Here we go. Green Honda Civic. Huh. I don't know anybody with a green Honda Civic. Okay. So magnitude of r prime of t is speed, and distance is rate times time. The rate is the speed. Magnitude of r prime of t. That's the speed times the time, which is dt. So when we do arc length, we add up just little bits of distance. So that's over curve, magnitude of r prime of t dt. That's the simplest line integral that we know. Because we're just summing up arc length along a line. And the notion is that we're not actually on some axis. You know, in the past, when you did a single integral, you always integrated with respect to x, and the bits of x were on the x-axis. Here, there's no axis that I mean, obviously somewhere there's a coordinate system if we're doing this. But this arc length integral here is sort of defined independently of a coordinate system or an axis. You're just chopping up an arc and adding up the lengths. So because you're moving along an arc as you add this up, this is a line integral. It's almost like better to call it a curve integral, if you know what I mean. But they call them line integrals. Okay, so that's the oldest type of line integral. So if we sum up some function as a position on arc, along an arc. Sorry, I should function of a position on an arc. Call it C. then a line integral can look like this. You can have an integral of some function in 3 space or 2 space. So you're evaluating at points on a curve and then multiplying by arc length. So I'm done. So the notion is, the idea is every point on the curve has x, y, z coordinates. And you're going to evaluate this function at that point and then multiply by the associated arc length at that point. Okay. Now, this has to be sort of defined in terms of what does that mean. So I would just say, let's go ahead and define all of this. So what we mean when we say this is that x is really x of t, y is y of t, z is z of t, and as you know, ds is the magnitude of r prime of t, dt, where t is going to range from a to b. Okay, so let's go ahead and put all of this up above here. R of t has 3 coordinates, x of t, y of t, and z of t. Like that, where t is going to range from a to b, and that defines curve C. So you'll have to have the curve defined somehow, usually parametrically in 3-dimensional space, but it doesn't have to be parametrically defined if you're in 2-dimensional space. Okay. So just as a note, if F gives like a mass density of the curve, then the integral is mass. But we can also compute moments and moments of inertia and center of mass for a curve. I'm going to say first and second moments. And center of mass. Okay. Any questions? And I'll leave the formulas for all that to your imagination. I think the book does. I'll do an example of one just to kind of help you see how that would go. But let's go ahead and do a couple of other line integrals. These come up in homework problems, but I don't have direct applications other than they are part of an integral that's a vector integral that we'll be doing shortly for computing work, which is, as you know, energy expended by a force as it moves an object. Okay, so other line integrals, these are components of work. So you could have this kind of integral along a curve. So you'd have like an integral of f of x, y, z, and then you could just do dx. And you could do this with y or z as well. So f of x, y, z, and then you could just do y. Same thing with z. Okay. These, like I say, these end up being components of a sort of a vector integral when you compute work. So you may as well understand what they mean. They don't have importance for their own sake, I don't think, but mostly when you compute work or other similar integrals like circulations and other example of this. Okay, so here, same thing. You would do f of x of t, y of t, and z of t. And for dx, you'd have to say x prime of t dt. Okay? And t would still go from a to b. So all these are similarly defined. Okay, so let's just make a note. These are components of a so-called work integral, which is which will come up later. Okay, probably owe you guys some examples. Okay, so let's real quick do the, let's say, suppose that, let's say, delta of x, y, z is equal to y squared z, gives mass density of a thin curve. Well, let's just say it's a wire then, like a thin wire at the point x, y, z. The wire follows curve C, which I'll parameterize to be, no, we will parameterize, but let's say C is just a line segment from 312 to 125. Okay. So we're going to have to parameterize that. Any questions yet? I don't see any questions. Just pipe up and say something, or feel free to text me if you have something, or chat me. Okay, so first of all, we're going to need to parameterize the curve. So remember R of t, I think we said it was R0 plus like an R1 minus R0 times t. And when t is 0, then you're at R0. And when t is 1, I think the R0 is canceled and you're at R1. So t would range from 0 to 1. So let's see here. R0 would be 312. Plus, let's do this in our head, R1 minus R0. So 1 minus 3 is negative 2. 2 minus 1 is 1. 5 minus 2 is 3. and that's times t. Okay. So maybe we could write this as 3 minus 2t, 1 plus t, and 2 plus 3t. Okay, and you may remember when you do this method to parameterize a line, t always goes 0 to 1 if you want to go from one point to the next in 1 second. Okay, does anybody have any questions? Okay, so we'll need our r prime of t. So do remember any mention of x at this point refers to the x coordinate on the line. So that's x, y is the second, and z the third coordinate. Okay. So the mass of the wire is the line integral along curve C of the density function delta of XYZ. So you're multiplying mass density per unit arc length times arc length to get mass. Okay, does that make sense, everybody? Mass per unit length times length. Okay, and then the rest is just plugging in. So, so delta is, and I'll keep the abstract notation here. Over curve C, delta was y squared z ds. And then we'll remind ourselves, maybe up above, that r prime of t is the vector negative 2, 1, 3. Okay, so you'll need that. And then the magnitude of r prime will be the square root of negative 2 squared plus 1 squared plus 3 squared. So what's that? Square root of 4, 5, is that 14? Okay, so any questions about this? Is, you know, to do arc length, you need the speed. You need how fast you are going, and then you multiply that by time. Okay, so questions? All right, so I think we can go straight to the integral now. Y is 1 plus t. You have to square that, multiply by z, which is 2 plus 3t. And then ds is the outright magnitude of r prime of t, dt. And t will go from 0 to 1 on this. Okay, any questions? So these are the whole chapter, by the way. The main new integrals you learn are line integrals, and then later on surface integrals. So you've done integrals through solids. That was a triple integral. Now you're doing integral. These we want to basically be able to integrate on any shape in any dimension. A line integral integrates in one dimension on a curve. A surface integral integrates in 2 dimensions on a surface. And a triple integral integrates in 3 dimensions through a solid. So that covers every possible shape, and that's kind of the gist of what this chapter does, is it gives you the ability to sum up something, usually mass density or for moments. through any object, be it 1, 2, or 3-dimensional. And I guess you could be 4-dimensional if you want to talk about that kind of stuff. But again, this is sort of your last computational tool in calculus, just to be able to sum along any kind of object. And then that just gives you the ability to set up all kinds of crazy problems in physics and other settings like that. Any questions? All right, so this is going to be a little painful. I'm just going to shut my mouth off for a minute and hope I can do this without screwing up. So I'm not entirely confident that everything's perfect here. So I'm hoping you guys, as you work this, obviously do let me know if you see a discrepancy. Am I frozen? Somebody said I'm frozen. Okay, so there we go. That's obnoxious. Okay, so now I'm going to try and evaluate this.
Don't forget the square root of 14, Professor.
Oh, thank you, Alicia. Okay, so I get 107 over 12. So it would be 107 square roots of 14 over 12. That's what I got. And I hope you don't mind that too much. And if I'm close, I feel pretty good about that. Any questions or complaints about this? Okay, so that's a mass. Just real quickly, just make sure you do it. So if we want to do moments, You'd have like a moment to the xy plane, which would have a line integral along the curve of, you'd have to do z times density ds. Okay, let me fix that. Like that. And then the rest is kind of obvious. And then the center of mass of a wire, they have centers of mass. So this would have 3 coordinates, x bar, y bar, z bar. And then, of course, x bar would be m y z over m. Y bar would be m x z over m. And, of course, z bar would be m x y over m. So those are all similar formulas, but you're just summing in one dimension. And I guess this could easily be a surface instead of a line. And when we do a surface integral, I'll change to the lowercase s for arc length to a capital S for surface area for the differential. And the single integral will turn into a double integral, and you'll sum over a surface rather than a curve. So these will essentially be the same formulas when you do the mass or the moments for a surface. A curved surface. Any questions? Okay, and I'm not going to do any more of that. Let's do this, just another example here. So we're going to do the integral of x squared plus y squared dy. For the curve C, where C is defined as y equals 3x squared minus 4, where x is going to go from 2 to 5. So this is a two-dimensional curve. Well, there's no mention of z anywhere. And the curve is defined two-dimensionally. Okay, so you have to take the differential in the context that it's given in. So here you would say, and these are all just about substitutions. If y is 3x minus 4, then dy has to be y prime dx. Okay, so here you'd have to say 6x dx is going to be dy. Okay, so you see that dy there. As a matter of fact, this whole integral has to be a function of x because y is a function of x. Okay, so then you just come back and you're ready to pound this out now. You're going to see x squared plus y squared, but y is 3x squared minus 4. You can't have two independent variables. There can only be one independent variable here. So then that's squared. Okay, and then the dy gets the 6x dx. Okay, does that make sense? So again, this is ugly, and x will go from 2 to 5. So I don't know, it's just substitutions and a regular singular integral. So it's not hard. You just have to sort of get over the notation. Okay. Somebody was asking me the other day about what CAS can I use now that we're doing triple integrals. I'm gonna show you. I've been all over trying different things. Maple you know, like I said, Maple's $100 unless I can get you a discount. Nobody's asked about that, so I'm not worried about it. Mostly people want free things these days. Just real quickly, let me show you something that's about $10, but you need an iPad for this. Let me get it real quick here. This is the TI Inspire app. It's a little slow, so it's launching right now. I think it's launching. Let me stop this share. Yeah, it's still launching. So as you know, TI Inspire, you probably know, TI Inspire is a graphing calculator, but this one has a CAS, which is a computer algebra system, and that's super, it's really good. So I just thought, well, let me show you what this one does. So I'll share this with you real quick in a moment, as soon as I figure it out. Okay, here's my TI Inspire. It's just a calculator, but it's pretty great. So I'm gonna go, what if I can just click on this. So I'm gonna add a calculator to my document. So I just clicked on that. I also do an integral. So just like it's a calculator, this thing I decided is just as good as most of the computer algebra systems out there. So in the menu, I see there's a calculus menu, and I want to do an integral. So, and even with limits, so you can delete those limits. 2 to 5, and this thing is x squared plus open paren. I'm not even here. I'm just typing on my keyboard. 3x squared and plus 4. Okay, and that's squared also. Okay. And then outside of these parentheses is a 6x and then a dx. Okay. And so I don't know if you can see it, but oh, what a mess. I'm just going to write that in. So, but that's a $10 program right there, and it'll do triple integrals with variable limits. So it's a little hokey, but $10, you know. Let me go ahead and, but again, it's an iPad program. Oh no, I lied. No, I'm running it on my Windows machine, but it's more expensive on the Windows machine. It's only $10 on the iPad. Okay, so backpedal. It's more, you have to get on the TI website if you want the Windows or the Mac version. All right, let me go back to my iPad. Okay, so just a real quick jump back here. That came out to be 327,789 over 2. Beautiful. One more integral that I know I could do. But why in the world would I do that integral by hand? If I've got a device that'll do it, and certainly I know how to evaluate single integrals. Here's another crazy problem. How you guys doing out there? Let me look at the chat. Looks like everybody's okay out there. Okay, that's fine. Let me go back to, just one sec. We're going to do one more problem before we go into the vector one. Okay, so this one says we're going to find the moment of inertia. about the z-axis. For the helix, let's say the helix along curve C which is parameterized by R of t. The components are 2 cos t, 2 sine t, and t over 4. Where t is going to range from 0 to 12 pi. Okay. With mass density delta of xyz is just z over 2. Okay. So again, this is a single integral. You got to get it down to one variable. And of course, it'll be t this time. We're going to need to multiply by arc length. So arc length needs the speed. Let's go ahead and do r prime of t first thing. So this would be -2 sine t, 2 cos t, and 1/4. Okay. And then we need the speed, so that'll be magnitude of r prime. What is that, like 17 over 16? No. 4 is 64. So is it 65 over 16? Which is the square root of 65. Divided by 4. No. Any questions? So that's the speed. And the distance is rate times time. So we have the rate. If we multiply by time, we'll have distance. And if we multiply that by mass density, then you have mass. And then we'll have to multiply by distance squared to get a moment of inertia. I think we got everything we need here. So remember, when we refer to x, it'll be 2 cos t. Y will be 2 sine t. And z will be t over 4. Okay? And so the moment of inertia about the z-axis is going to be, we have to do distance squared to the z-axis. And you may remember from xyz, the distance is the square root of x squared plus y squared. That's the distance to the z-axis. But if you square that, you just get x squared plus y squared. So that's the distance squared. And then times the mass, which is mass density at xyz, times arc length ds. Okay, so that would be a general formula for the moment of inertia about the z-axis. Don't forget, ds here is r prime of t dt, magnitude r prime of t dt. Okay, so here we're going to jump in and say, well, this along C, this is x squared plus y squared Delta is going to be z over 2. And times ds, which is the magnitude of r prime, times the square root of 65 over 4, and then dt. Okay? Any questions? Then maybe worth noting up there that x squared plus y squared is going to be 4. So I don't know what it is. I would do that. So here we go. Integral. So x was 2 cos t. So it'd be 2 cos square 2 cos t squared. So that's x squared plus 2 sine t quantity squared. That's y squared. Z over 2 is going to be t over 4 over 2. Because z is t over 4. Okay. And then square root of 65 over 4. dt. Now everything's in t, so we can say t is going to go from 0 to 12 pi. Okay. This whole thing with the sine squares and the cosine square, that's just going to be 4, the whole thing, right? So I think you end up, what if I did this? Integral from 0 to 2 pi is just a 4 times a t over 8 times the square root of 65 over 4 dt. 4's will cancel. And maybe we'll bring the square root of 65 over 8 out. Oops. So we just with an integral from 0 to 2 pi of just t dt. So here you'll get a square root of 65, and there's a half t, so that'll be over 16. Do t squared from 0 to 2 pi. So we'll get a 4 out of that. 4 pi squared. Let's just write that. So it's the square root of 65 over 16 times just 4 pi squared. So maybe we'll finish it up and say square root of 65 pi squared. 4 and 16 goes 4 times. Oh, I got the limits wrong. Darn it. Okay, hold on. It should be to 12 pi. So, but yeah, thank you, everyone. This should go to 12 pi, not 2 pi. So let's put those in. Okay, so that 4 is going to be a 144 instead. So it's a 144 pi squared. 16 goes into 144 9 times. So this will be 9 square root of 65 pi squared. Okay. Thank you for your help on that. Any questions? So that would be a moment of inertia That's just a, remember, resistance that measures inertia for spinning. That is a resistance to a torque. Okay, any questions? What time is it? 6:54. Let's go a little bit longer. The last part of the lesson is work. And there's actually, this is actually super easy. So we'll do a couple of these. Yeah, got a couple. So let's do just a reminder that work is force dotted with displacement. And this would be linear displacement. So that formula doesn't work on a curve. And yet, if a force field moves something in a curved path, there ought to be a way to compute the energy that's expended to make that motion. Okay, so what work is done on the object when you don't move in a straight line? Well, here's the idea. We do it on a small scale, as always, in calculus. So here's a point and a very small displacement that we will call dr. This is our differential displacement vector. Okay. And just as a reminder, that dr, if you take the magnitude of dr, well, first, hang on, a couple things. First thing is that dr is r prime of t dt, and that the magnitude of dr is ds. So these two differentials, one's a vector, but right now I don't want arc length. I want displacement as a vector because I need a dot product to compute the work. Pardon me, no, it's not. So it seems to me quite straightforward. This is curve C, which might be parameterized by some R of t, where t ranges from A to B. And so work would just be, you take force dotted with displacement, and my displacement is a differential displacement. So that's differential work. I would need to add that up over the entire arc with a line integral. If I'm adding up along an arc, it is by definition a line integral. But now I'm not adding up bits of arc length. I'm adding up over bits of displacement and computing the work at each point on the curve. Okay, so, and just remind yourself, this is actually an integral in t, because just remember, dr is r prime of t. Now that's a vector, but once you do the dot product, it'll be a scalar. Okay, does anybody have any questions about this? Okay, well, let's do a quick example. Or two. Okay, so real quick example, and I kind of want to go back to that field that we did. There's a couple of examples I want to do. So let's remind you, I'm going to go back to the previous lesson real quick and grab the field that we started the discussion with. This guy. And you can just do a quick sketch just to kind of show this swirling effect of the field. I call this, sort of either a tornado or a whirlpool. Okay. Let's do our curve as just a circle. Okay, so we're going to do a circle of radius 2. So R is going to be, RT is going to be 2 cos t, 2 sine t, where t is going to go from 0 to 2 pi. Okay. So what color will this be? I'll do purple. Yes, so I'm just doing this curve. This is not great. See if I can put it into position here. Yeah, it's pretty bad. Actually, I'm going to center it on the origin just because it's no other hope. There we go. And notice there's sort of a direction associated with this. Time increases and the curve is counterclockwise. It's actually going in the same direction as the field. So we're spinning around counterclockwise. If you go, and because you go in the same direction as the field, the work is going to be a positive number. If you go against the field, the work comes out negative. And that's what happens is when the field does work on you, like you're falling, you lose potential energy and the work is positive. So work is positive whenever your potential energy goes down. Okay? Work is negative when you gain potential energy. If you go against the field, your work will be negative. So, it's like if you're lifting something up, then gravity is doing negative work on you as you push something up against gravity. And you're gaining potential energy because of that. Any questions? So we're moving around this circle, C. All right, let's set up the integral. And we're going to need our dr. So real quick, let's do dr. This is just r prime of t dt. And of course, that's a simple computation. So we'll do negative 2 sine t and 2 cos t dt, like that. And let's just go ahead and do this. F integral, let's just say work, is the integral over the curve of f dot dr. Okay. So maybe a couple of steps here. Let's just write the integral with the field in it, which was negative y over 2 x over 2. Okay. And then I'll say dot dr over the curve C. Okay, so that's a vector integral with a vector differential. Now it's time to do substitutions. Just keep in mind any reference to x is 2 cos t, and any reference to y is 2 sine t. Okay. So I think we can go ahead and do this. So the vector negative y over 2, that'll be negative 2 sine t over 2. And then x over 2, that's 2 cos t over 2. And then we're dotting that with dr. dr is negative 2 sine t. And then 2 cos t dt. Okay? Do the dot product, and this will be an integral in t, where t goes from 0 to 2 pi. Any questions? This is easy now. So you're just doing, first you get some cancellations. I think you're going to get integral 0 to 2 pi. It looks just like 2 sine squared because a bunch of 2's cancel. So you're just going to get 2 sine squared t. Actually, let me factor the 2 out. So you have 2 and then sine squared t plus cos squared t. Like that. And that's just a dt. Sine squared plus cosine squared is 1. Integral of 2 will be 2t from 0 to 2 pi, so I think that's just 4 pi. Now, something's funny about this. Those of you who've studied your physics know that if you move an object along a path and it turns out that your ending point and your starting point are the same, the work should be 0. And that's not happened here. And that's because this field is what we call a non-conservative field, meaning there's no conservation of energy here. What's essentially happened is the field has done work on me, and I'm still in the same position, which means I haven't lost any potential energy. That can't happen. Okay? When a field does work on you and moves you, in what we call a conservative space, a conservative field, then work always results in you losing potential energy. Right now, I can't have lost potential energy because my start point and my end point are the same place. So energy has been expended, but my potential energy did not go down, which is another way of saying energy just appeared out of nowhere. It was created. And energy can't be created. Well, it can in a non-conservative field. So this field is not conservative, and that is why we're getting this weird result. Let me do one more quick example before the break. Okay, so here's a different field. This one's 3-dimensional. F of xyz is going to have the first component be z squared, second component x squared, third component y squared. C is a line segment from 100 to 412. Okay, so this is a force field. And so the question is to compute the work done by F. Remember, work is just energy. Am I frozen? Oh, dang. Okay. so I'll just pause here for you. I'm just gonna hold on for a minute while you copy this down. Okay. So let's just jump right into this. We're going to have to get this line segment. So the first position vector here we'll call R0. The second position vector is R1. So remember how to parameterize a line segment. R of t is R0 plus R1 minus R0 times t. And t will go from 0 to 1. So anyway, this is 1, 0, 0. Plus 4 minus 1 is 3, and then the rest is a 1 and 2 times t. So this will be 3t plus 1, t and 2t, make that. And then dr is r prime of t dt, okay, which will be just 3, 1, 2, I guess. dt. Don't forget, when we refer to x, x will be 3t plus 1, y will just be t, and z will be 2t as we go through this integral. And again, line integrals are just substitutions, okay? So, here we go. We're supposed to do the work, which is always just an integral of a field dotted with displacement. Okay. Okay, and then we've got the field, so maybe we just start putting stuff in here. F is going to have a z square, x square, y square, and then dot that with dr. And then it's time to bring out the brass tacks. So we have an integral. Z is 2t, so that's going to be 4t squared. X is 3t plus 1. 3t plus 1, that'll get squared. And then y squared, y is 2t, so this would be, no, y is t, so this would be t squared. And then dotted with dr, which is 3, 1, 2. And that dt. And t is going to go from 0 to 1. Okay. And now it's dot product and then just a little bit of work. We get 4t squared times 3, so it's 12t squared plus, let's see, a 3t plus 1 squared plus a 2t squared. Okay, dt. Okay, and here we go. think it's 23 t squared altogether. And plus 6t plus 1. So that's 4, which is 12 thirds. That's 23. I think it's 35 over 3. Okay. Maybe just a quick reminder of units. Okay, I'm going to pause. Any questions about that? So I didn't do anything with units, and I apologize. I feel bad. But so in metric, you would do meter, well, Newton meters. Which is joules, Joules. Newton, that's your force. Meters, that's your displacement. Okay. And then in imperial units, we'll try that again. Then it's foot-pounds. So the force is pounds, and the displacement is feet. And foot-pounds are just foot-pounds. Okay, and that's a measure of energy expended to move a pound, the distance of a foot. Sorry, move the distance of a foot with a 1 pound force. Okay. That's it for that lesson. I think it's a good time for our break. So let me stop the recording, and if you have any questions, hold them for a minute, and I'll see you guys in 10 minutes. We had a couple of notes to the notation that we've just gone through. A reminder real quick that, first of all, dr, we said, is r prime of t dt. So r prime, if r has 3 components, x, y, and z, then these would be x prime of t, y prime of t, z prime of t, and then with the dt out here, you can think of this as x prime dx, comma y prime dy, comma z prime d. Oh, forgive me, I'm screwing this up. I'm gonna erase all that because I screwed up. Okay, so it's x prime of t dt, y prime of t, sorry about that, dt, and z prime of t dt, like that. And I just want to say x prime of t dt is just one way of describing the differential of dx. And differential of dy is y prime dt, and then dz is z prime dt. Okay, so those are all different ways of writing what dr is. And that comes up if the force field that we're integrating through has component vectors. I think we talked about p, q, and r in 3 dimensions, all functions of x, y, and z. Very frequently, it's just too many notations. So we'll just start saying, okay, let's just call it PQR and understand that these are functions of X, Y, and Z. Sometimes I'll just say F even and not say the X, Y, and Z. Okay, but we just need to understand that we mean these are all functions. And then when I do F dot dr with a line integral, I just want you to see the alternate notation. Sometimes they'll write that, you know, well, the dr is PQR. Sorry, the F is PQR. And then the dr you could express as dx, dy, dz, like that. And you'll see problems in the book where they have just p dx plus q dy plus r dz. And even though there's three differentials and they're different, they're all part of a single integral. So you'll see stuff like this in the book, okay? And you just need to note that these are equivalent. And if the integral of f dot dr is weird to look at, this second form that I've just given is even weirder. And you just need to sort of be prepared to reinterpret one as the others. These, again, are equivalent. And in both cases, I would consider them a work integral. Okay. And when I was at the very beginning of this lesson, I was saying, okay, when you see something like, let me just go way back to the top here. These integrals, the integral with a dx, the integral with a dy, or an integral with a dz, but those are actually components of a work integral that has three parts with a dx, a dy, and a dz. And so you'll see stuff like that in the book. Okay, just remember it's a work integral. Okay, and everything ends up being an integral really over time, because everything's a function of time here. Okay, so enough of that.